ideally, this is what I would like to see. Okay?
And remember that Minskir's result gives us something which is not quite sub-Gaussian, even though it kind of has that form. All right. So I will do this slowly in various steps. And first, we will construct an estimator that works when the distribution is spherical. What does spherical means? Spherical means that the trace is about d times the largest eigenvalue. Okay? So if all eigenvalues are about the same order, okay, that's what we will. I'll make this this definition. I will make this definition more precise. Okay, so here's what we do, and then those of you who are interested in algorithms will get horrorized immediately. So here's what we do: we take the set of all unit vectors, and we take a 1/2 cover of that. So what's a 1/2 cover? It's a subset. So these are unit vectors in Rd, such that for every vector, every unit vector, there exists an element in this cover that's within Euclidean distance 1/2. Okay. All right. So we just want to cover the space. The minimum cover is known to be not larger than 8 to the d. Okay. So we take exponentially many of these guys. Right? So this is not computationally efficient in any way. Right? We take an exponential, such a discretization of the unit vectors, and now we're gonna project the vector to each one of these directions. Okay? So we look at the inner product of such a vector with x. Okay? That's the mean, and we can calculate the median of means estimator of that. Okay? So in each of these exponentially many directions, we project. We have a one-dimensional problem, and we know what to do there. Okay? So instead of doing the coordinate-wise thing, we now cover the whole thing, the whole space. Okay? Good. Now, the variance is always bounded by the largest eigenvalue, clearly, okay, of the matrix. And therefore, from the median of means bound, we immediately have that if I now, you see, I want to use the median of means estimate. The median of means estimate, this guy. I'm going to use it not with the parameter delta, but the parameter delta over 8 to the d, because I'm going to use a union bound over these 8 to the d directions. Okay? So then I'm allowed to take this supremum. So with probability at least 1 minus delta, this guy minus the true mean is bounded by, and this lambda max is the same lambda max for every direction. Okay? So this is what we get immediately from the median of means estimate. Okay? So there's some constant and square root of the variance, right? The variance times the log 1 over delta, and now 1 over delta is 8 to the d over delta. So this is going to become a d plus log 1 over delta divided by n. Okay? So this we know that this happens, that the true mean satisfies this inequality for all 8 to the d directions. Okay? Good. But now this defines us a polytope, right? Now I can take all those x's, right, in each direction. We have something like this. So in each direction, I know that the mean is somewhere in this stripe, right? And now for another direction, will give me this bound. Another direction will give me this bound. Okay? So we have a polytope, which is the intersection of all these. And we know that with probability 1 minus delta, the true mean is in that polytope. Okay, so this is the polytope that's defined by all these stripes. Okay? Yeah, so far so good. Okay, so these are just the confidence bands that we get in each direction. Now, so with probability 1 minus delta, mu is in here. In particular, with probability at least 1 minus delta, this polytope is non-empty. Okay? Because the mean is there. So our estimator is we just pick any of the elements. So we know that with high probability the mean is here, so just pick any element you like. That's going to be our estimator. Okay? And then it's really easy to see that, okay, so this is our estimator. There's one catch here, is that this polytope now depends, you see, the polytope here that we're really interested in depends on the largest eigenvalue of the covariance matrix. Okay, but we don't know that. So for each lambda, for any lambda we can calculate this polytope, but let's assume that lambda is greater than lambda max. And in that case, everything is true what I just said. So we look at the polytope. This polytope, then it's going to be non-empty, and we can pick one there. And now it's really easy to see that that if our within that polytope, this is our estimator. The true mean is somewhere in here. But it's very easy to see that the distance of those two cannot be larger than this. Okay? All right? So, good. Now, this is not lambda max. But if this is not much smaller than twice lambda max, then this is the right thing. Okay? And in particular, if the distribution is spherical, if the distribution is such that the trace of the covariance matrix is larger than some constant times d times this lambda max, then is this right? I guess it should be. So the trace is always less than d times lambda max, right? But now we want to we say that if it's larger than some constant times that, then we get then this is actually of the correct form, right? Because we have lambda times d here and lambda here. So lambda times d in this under this spherical assumption is really the trace. Okay. So just by doing this simple median of means estimator in each direction, picking one element from the polytope we get. If we have a good prior estimator for the largest eigenvalue, then we can construct a truly sub-Gaussian estimate. Okay. So there are two big assumptions here. One assumption is that we know lambda max up to a constant factor, and the other one is that the distribution is almost spherical. Okay? So all eigenvalues of the covariance matrix are about the same. All right? Okay? Good. So this is nice, but not completely satisfactory because of these bounds, of course. Okay? Now we will work hard to actually get rid of these assumptions. Okay? I'm really interested in this challenge. Come up with something that doesn't do this discretization. Yeah, I don't know. Okay, so what do we do now? How do we extend this to general distributions? Well, we try to decompose the space into orthogonal subspaces such that the projection of x into each subspace has a spherical distribution or nearly spherical distribution. And on the way, we will also construct estimators of this lambda max that will allow us to do this. Okay, that will allow us to use the previous bound. Okay, so what we're trying to do is trying to get some kind of a decomposition of the space into orthogonal subspaces. The projection into each orthogonal subspace of x has a nearly spherical distribution, so we can estimate the mean in each of those guys, and we will just add them. Okay, so that's the plan. This won't come for free. We need a higher moment assumption. Okay. This 4 can be replaced by anything that's larger than 2, but that's not too important, at least to me. And in any case, we do need something. So for Minsker's inequality, and also for this bound, for the spherical case, we didn't need anything else. Okay? These were here we needed a bound for the variance. For Minsker, the Minsker's bound, we didn't even need that. Okay, so we are adding a little bit of conditions here. And okay, so here's what we do. Again, we discretize. So this is now we actually have to discretize even a little bit finer. It's not going to be 1/2, but still some constant. So this gamma is a constant. Think about 1/10 or something like that. We take such a discretization. It's still exponential, exponentially many directions. And in each direction, now we calculate an estimate of the variance. Okay, so this is just the variance of the projection to the direction of u. Okay, and this can be done because the variance can be written in this form, right? If x and x prime are independent, identically distributed vectors, then this is the standard, right? The variance equals the expected 1/2 times the expected value of x minus x prime squared. So that's what we use here. And now, for this, we can get samples by splitting the sample into two. Okay? So we have these independent, identically distributed data that have expected value, which is this quadratic form, which is the variance in the direction. And now we in each of these directions, we construct the median of means estimator. Okay? And since we have this upper bound, this condition, we have a good guarantee for the quality of this estimator in each direction. Okay. And now we calculate the sorry. All right. So now what we have is a polytope of covariance matrices. So again, the same kind of argument as before. So we have this discretization. The true covariance matrix is such that that for each direction it's gonna be for each direction the value of the quadratic form is not far from the estimated value. So now we get the same kind of stripes as before, but now in the space of the covariance matrices, which is non-empty with probability 1 minus delta, because the true covariance matrix is there. So we just pick one covariance matrix from there. That's going to be our empirical estimate. Okay. So this is repeating the same kind of ideas. This is how we construct an empirical covariance matrix. A really complicated way, but forget computations. This is really an information theoretic construction. And now we have this estimated guy, which exists with probability at least 1 minus delta, and now we can compute this is gonna be positive semi-definite, and so we can compute the spectral decomposition of this, order the empirical eigenvalues, and now our subspace, our first subspace, is gonna be the subspace spanned by the eigenvectors that correspond to the eigenvalues that are between the largest and the largest divided by 1/2. Okay, so we're going to take an exponential step. Okay, so we take only those eigenvalues, eigenvectors whose eigenvalue is large, is among the largest. Okay? And we take the space spanned by those eigenvectors. This is going to be our first subspace. With a little work, you can prove that in fact, this lambda 1 is a good estimator of lambda max. Okay? It's good in the required sense, so it's within a constant factor with high probability. with probability 1 minus delta. And yeah?
What is the difficulty here? If you don't care too much about computation, you can just, basically achieve that, right? You can achieve the guarantee of lambda 1 hat. So what is the difficulty in showing that lambda 1 hat is true, is close to the truth?
Lambda 1 hat. Well,
so what's the difficulty in showing that this is close to lambda 1?
It's not. No, it follows from the previous. Well, you have to pass from the discretization to the non-discretization.
Okay.
But yeah, it's not easy. It's not difficult. Okay? But it's you can. That's really not hard. So this is going to be close to lambda 1 within a constant factor, and therefore, or also, this space, the projection to this subspace of X is almost spherical. Okay? So at the end, I'm going to split the data in many different chunks. Okay? So in the first chunk, we do this eigen decomposition, and in the second chunk, we will use our estimator that works for each projected subspace. So this was the first step. On a chunk of a data, and now I take fresh data, and on that fresh data we project everything to this empirically chosen subspace, and we work in that. But now we have independent new data, so I can repeat the exact same procedure. Okay? And I will do this in order log d steps, okay? Until we get down to a value such that the largest eigenvalue is already of the order of trace divided by d. Or largest eigenvalue divided by d. In that last subspace, I don't care. We can just use Minsker's estimator. Okay? Because in that space, the eigenvalues are already so small that Minsker's estimator gives us the right value. Okay, so this is the very high level idea. And at the end, here's what we get. Okay. I said that. So this is what we get. With probability at least 1 minus delta, our constructed estimator differs from the true one by not more than a horrible numerical constant. This is really just a universal constant. And now, this is really what we want to see, except for this log d. Yes?
Can you just make sure I understand? So Minsker, that log d was actually a log d? Was that the difference? Or?
In Minsker, you have essentially, so you have the trace here.
Oh, okay.
Which is like d times. You have a d times this.
Okay.
Okay, and here you have a plus log d. I can live with this plus log d. It's not really dimension free, but okay. For all practical purposes. This is not an issue. What is an issue is that in order for this to work, I need n to be non-trivially large. Okay? So it has to be at least d log d. And this is not completely clear that this is necessary. Okay? And this part comes in the construction, in the eigen decomposition. But if n is at least d log d, then we have a nice sub-Gaussian behavior.
Don't we need at least some dependence on d, like linear dependence on, for example, to be able to say anything about the L2 distance between the data and the...
Not according to Minsker, right? It only depends on the... it's completely dimension-free. It works in an infinite dimensional space. It only scales with the trace. Or in the Gaussian case, it only scales with the trace.
Suppose you have just a binary product distribution in n dimensions. Let's estimate every coordinate independently, we estimate the mean vector.
Okay.
Already, any non-trivial approximation requires at least d.
Of course, yes. But dimension per se is not necessarily there. Right? It should be everything that depends on the dimensions should be somehow encoded in the trace of the coordinates matrix. If things were like they are in the Gaussian case.
So you feel that these things are like artifacts of the proofs, like this log d and the assumption of n?
I hope so. Yeah, I don't know. We don't have. This is very recent, so I don't know. But this comes in because we need independence. When we do these several steps of decomposing the space, then we need fresh data because, and this log D comes in there. This one is more essential. Yeah. Okay, so that's our final estimate. So as I said, it's sub-Gaussian, but not quite dimension free. Okay, and now I have until half an hour. Okay, that's good. So now I'm going to show you something completely different. Well, how to use this thing for empirical risk minimization. Yes?
About the less
yes.
So to have the asymmetry, you have to choose a point inside the solid token.
Right.
Which, even though if the dimension is very large, you have to run some kind of linear program.
Yes.
To deal with it.
Yeah, with exponentially many constraints.
With exponentially many constraints.
Yes. So it's a disaster. It's a complete disaster. But we have experts that are in algorithmic statistics. So yeah, I think it's a really nice problem to come up with an algorithmic version of this. Okay. All right. So here's an application. A natural application where mean estimation comes in a natural way, which is in statistical learning theory. So we have, let's say, we have a random variable that takes values in some space, we don't care, and we have a set of non-negative functions. These are some kind of loss functions, and we define the risk of each of these functions by the expected value of f of x. Right? So these are real valued functions, but we have lots of them. And now, ideally, we would like to find an f that minimizes this risk. Okay? That minimizes the expected. So think about this as some kind of loss. So one example could be in regression, where this f is some kind of g of x minus y squared, right? This would be the loss function, okay? Or in vector quantization or clustering, it's going to be something. So maybe if I have time, I'll show some applications, okay? But this is some kind of loss function. We want to minimize that loss function, right? And I will call this a risk. The expected value of f is a risk, borrowing the statistical terminology. Now, of course, we don't know what these risks are. All we have is an IID sample from this space, and we would like to find a function with the small risk. So what can you do? Well, you estimate the risk of each one of those and minimize that. This is called empirical risk minimization. This is everywhere in statistics, in statistical learning. Least squares estimation is an example of this. Okay, so usually, of course, you estimate these means by the sample mean. Okay, and we minimize that. Okay. So this is the classical empirical risk minimization setup, and I'm interested in the performance of the empirical risk minimizer. So this is the risk of the empirical risk minimizer, and it's a conditional expected value because it depends on the data. Okay? This is the standard bound that the excess risk, so the risk of our empirical risk minimizer minus the optimal risk in the class is bounded by twice the largest deviation. Right? This is really the simplest performance bound that you can have, and here typically you use VC theory, empirical process theory to bound this. Okay? So one of the standard bounds is Dudley's chaining bound that looks like this: that the expected excess risk is bounded by what's called the entropy integral, so 1 over root n times the expected value of the integral of the square root of the covering numbers of this class. So the larger this class is, somehow the larger the expected, this excess risk becomes. So these covering numbers are just the covering numbers of F. So this is the number of elements of F that we need, such that for each element there exists one in the subset that is within distance epsilon. Okay? This is the same kind of covering number that we talked about already. And the distance, the relevant distance is now this, the empirical L2 distance. Okay, that gives you this. Now for Dudley's chaining method to work, this is what you need. You need that the probability, that the estimated risk of F and the estimated risk of G, these are two candidates, differ by more than epsilon, should have this sub-Gaussian form. It should be less than e to the minus n epsilon squared divided by, and this is the distance between F and G. Okay? If you have this, then you can use chaining, and then you can get a bound. And it depends on for what kind of distance you can get this. You will get the chaining, the Dudley entropy bound in terms of that distance. Okay. So this is what you need. But if we have heavy tails, possibly heavy tails, if we don't have, so this is typically used in the case when you have either these guys are either Gaussian or sub-Gaussian or bounded. Then this works nicely.
And this capital D of Fg.
Yeah, that's in this case it's going to be okay. It's some kind of a distance. Okay. When you get this Dudley's entropy bound, then actually what you do is first you symmetrize, and then it's going to be actually this distance. So, but if this works in some distance, then you can use chaining. Okay, but these chaining bounds are very difficult. If you have heavy tails, then they are just not true. Okay. So what can we do? Well, then we would like to use one of our smart estimates that are sub-Gaussian sub-Gaussian even for heavy tail distributions. Okay. So median of means is of course the first thing that comes to mind, but we couldn't make that work. So that just seems hard. If you write down chaining, because of this difficult, the median of means, because of the median has this non-linear component that just makes this kind of bounds impossible to derive. So we couldn't make it work. Okay? And that is a real problem because if you don't have chaining, the only thing you can use is union bound, and then with union bound you can lose big orders of magnitude. Okay? However, Catoni's estimate in this case can be made. Okay? So this is one of the reasons why we like Catoni's estimate, because we could work out chaining for this. Okay? So remember that Catoni's estimate solves this equation. Okay, so for each mu, we can calculate this function where phi is this increasing function, symmetric increasing function, this guy, and the estimator of the expected value of m sub f, the expected value of f of x, is going to be just the value of mu for which this equals 0. And here I'm going to choose this alpha this way so that it doesn't depend on delta. Remember that if you really want a sub-Gaussian bound, then the optimal form of alpha should depend on delta. But let's forget about that problem. If we choose this parameter this way, then we still have a sub-exponential performance bound. All right. This V is an upper bound for the variance, so that we will still need. Okay. All right. So now the empirical risk minimization is simply choose the f that minimizes Catoni's estimate. Okay. So for each f, we calculate Catoni's estimate, mean estimator, which is already a convex optimization problem. We solve it, and now we choose it over all f. So here's another computational problem under some special cases can you compute this efficiently? That's. But what we were interested in here is what can we say about the excess risk in general? So just the information theory. So if we have a finite class, then we can use the union bound, and then we get something like this. We can also do this for the median of means estimator. This will work, but this is not satisfactory. It's not going to give us optimal bounds. Okay. So here's what we could derive. Okay. It's a little bit ugly, but let me try to explain. So we need to assume that the variances of each of the f of x's are bounded. Okay? And which is fine. What's not so fine is that we actually need to know this bound. Okay? But let's assume that we know this bound. And in that case, we could get something that that doesn't require any condition, any other condition. Okay? So all we need is that these variances are finite. And then what we get is a bound that has 3 terms. So first of all, it has this sub-exponential term that we don't have the square root here, but that's because we didn't want to complicate our lives, and we chose that alpha, the parameter of Catoni's estimator, as independently of delta. So this is the price that we pay for that. Square root of v over n. This is fine. This doesn't depend on the. We would get this even if we had just one. Function in the class. Then we had something that looks really good. This is Catoni's. This is the like Dudley's chaining bound under this distance. So this is the expected square distance, which is really nice. And then we have a third term, which is of the smaller order. Okay. This is with the 1 over n. This is with the 1 over square root of n, so it should be of a smaller order, and very often it is. However, this guy uses the covering numbers in the supremum norm. And that requires the class to be totally bounded, which is not so good, but in some cases it can be made work. Okay, so this slide just repeats what I just said. So this is the main term, and then, but this guy requires f to be totally bounded in the supremum norm. Now we can weaken this, and we can have another version of the same theorem that replaces the second 2 terms by the 1 minus delta over 2 quantile of this empirical chaining. Empirical entropy integral. Okay, so here, this thing is now a random variable. The covering numbers depend on the data. Okay, these are purely empirical, and now this entropy integral is now a random variable. We can look at the quantize of it, and this is going to be the 1 minus delta over 2. Okay. Right? And now there's no assumption about the total boundedness. Okay? However, if you really want to calculate this, it's not an easy, or estimate this in special cases. That's quite some work. So we used this previous form to work out some applications. So here's one application. Okay, so this is for L1 regression, and it's L1 because things come out nicely. So take, let's say we have these IID pairs of random variables. Okay. So these Z's are the observations and Y's are the real-valued response variables. And we have a class of candidate functions. Okay. So these are the functions that we want to use to predict Y. Okay. So we want to choose a function G such that G of Z is close to Y. And we will measure the risk in the L1 distance. Okay. This is the risk is the expected value of G of Z minus Y. And I assume that this class is bounded, is totally bounded. Okay. Good. Now, G star is the optimal guy in our class. And the statistical learning problem is to find a function that minimizes this, that keeps this excess risk small. So the standard procedure would be just choose the G that minimizes the empirical L1 distance, the empirical L1 loss. But if the Y's can have a very heavy tail, then of course these empirical estimates can be way off. And now, since we have lots of candidate functions, we won't be able to do anything. Okay? So Chebyshev doesn't take you anywhere. So we need here. It's absolutely essential that we have sub-Gaussian tail bands. Okay? So we can use Catoni's estimator, and the only thing we need to assume is that the Y has a finite second moment. Okay? And in that case, if we now replace the empirical means by these Catoni estimates and choose the G that minimize, these are the estimates for each G, and now minimize the L1, minimize this estimated L1 risk, then we get something like this. So we probably get at least 1 minus delta. We have this log 1 over delta term. This is fine. This is just the square root of the variance of y divided by n. And something that depends now only on the complexity of the class of the G's, okay? The class of the functions. These functions are bounded. The Y's are not bounded. The Y's can have a very heavy tail, but that completely disappears. So this, no matter how large the tails of the Y's are, as long as they have a bounded variance that's known. So this is the bound that we assume on the second moment of the Y's. Then we have this nice bound. Okay. All right. And it actually works in this little toy example. Go through this. So we generated the Y's as a linear function of the Z's plus heavy-tailed noise. Okay, so this epsilon I has the student D distribution with D degrees of freedom. As the parameter goes to 2, the tail really blows up. Okay? When it equals to even the variance is infinite, but we still get something. But you can see that when the tail is nice, then but vanilla means the usual empirical risk minimization. Okay? So just empirical sample means are used and minimized, and the Catoni means that we minimize these robust estimates. And you can see that as the tail of the noise becomes heavy-tailed, we really have a big improvement. Okay.
Can you say again what the axes mean? So the y-axis is that, I guess.
So this is the loss. Okay, this is the expected loss, expected L1 loss, and this is this is somehow how fat the tail of y is, of epsilon is.
So what does the number mean? Like what is the?
That's the parameter of the student T distribution. Okay. This is for sample size 50. Okay, maybe. Okay, there's another application here, but for clustering, but I'm gonna skip that and maybe just show you the references. That's okay. Okay, that's it.